Hello everybody and welcome to this featured special. Today we'll be talking about the properties of water and how exactly water gets its property from a chemical standpoint. So let's start off by looking at the chemical equation of water. So what is a chemical equation of water, you may ask? It is H2O, the very familiar H2O. Now what does H2O actually mean? Well, let's break it up and look at it. H is the hydrogen, that's our chemical symbol for hydrogen, and then we have O for oxygen. Then we have two hydrogens. This denotes that we have two hydrogens. Okay, now before we look at what the chemical properties of water are as a molecule, so this is a molecule, this is a molecular equation of water, let's look at what its components, what the properties of its components are. So what are the properties of hydrogen, what are the properties of oxygen? And that will help us understand the properties of water. So we're going to go ahead and delete all this and pull up the periodic table of elements. I'm going to assume that all of you already know what the periodic table of elements is. For those of you that don't know, it is a way of organizing. It is a way of organizing the elements that are known and unknown at this point, but we can predict their properties using this periodic table of elements. It was put together by Mendeleev way back when. And let's start off by locating hydrogen and oxygen on this periodic table. So over here we have hydrogen and we have oxygen here. I'm also going to assume that all of you know the basic structure of an atom, which is composed of a proton, which has a positive charge, a neutron, which has a neutral charge, and an electron, which has a negative charge. Okay, so let's start off by drawing water. Okay, let's start off by drawing the nucleus out, which is composed of the protons and neutrons. And in order to know how many neutrons there are, we obviously know that there is one proton because of our atomic number here, and oxygen has 8 protons because of its atomic number. In order to find out how many neutrons we have, we need to look at the atomic mass of this element. Now, over here, the atomic mass is not listed, but on most periodic tables, it will be listed in this section. And the atomic mass of hydrogen is approximately 1. The atomic mass of oxygen is approximately 16. So we'll just write that out. 16 AMU. AMU stands for atomic mass unit. And hydrogen has 1 AMU. Okay. I'm going to delete all that because now that we know our masses, we can continue. Okay, so we know that hydrogen has 1 proton and it has no neutrons because the atomic mass is 1. That's what the atomic mass is comprised of, just that proton in this case, but it will also have neutrons. And it has 1 electron because it is neutral. The reason why I'm drawing this circle out is it's a 2D representation of where you can find this electron. It's known as a shell. In reality though, this electron would be moving around this proton in a random manner, in a 3D manner as well. So it'd just be going around like that, maybe like that, somewhere. But it's going to be in this spherical vicinity. And that sphere right here is known as a shell. Okay, and now let's draw out our oxygen. Oxygen has 8 protons. 4, 5, 6, 7, 8. And then it also has 8 neutrons because it has approximately a mass of 16 AMU, atomic mass units. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, now that is our nucleus. Now let's draw out our electrons that go around or that orbit this nucleus. Okay, so it's really important to know that the first shell has a maximum of 2 electrons. You can only put 2 electrons around this first shell. So this is not quite yet full, and now if we were to do that, let's just say we'd have one here and here. And it's really important that since this electron is negative and this electron is also negatively charged, they repel each other. They don't want to be near each other. So they're going to be pretty close, pretty far away from each other, but pretty close to this nucleus because it's positively charged. And these are our first electrons per se. So this is approximately where they would be again. This is a 2D representation. And we have 6 more electrons. These 6 electrons would be in the other shell. And how did I know that it would be in the other shell? Well, number one, the first outer shell, has a maximum of 2 electrons. The second has a maximum of 8, and most of them also have a maximum of 8, and that's why it is known as the octet rule. Octet rule. So, octet, and oct meaning 8. So that would be the octet rule. Okay, now let's draw our other shell. So 1, maybe another 2, 3, 4, 5, 6. Okay, so let's say those are our 6 electrons that are orbiting this nucleus along with these inner 2 electrons. And these outer electrons, these outer 6 electrons, are known as valence electrons. And these valence electrons are how we determine most of the properties because they dictate the reactivity of an element. Okay, so now that we have that, we know that there are 8 total electrons here. And now if you guys were thinking about this while I drew these structures out, you can see that over here we have numbers that show our periods. These are known as periods. So we have period 1, we have period 2, period 3, period 4, so on and so forth. And these are our groups right here. So group 1, group 2, so on and so forth. And what does this mean? So each of the following groups have the same number of valence electrons. They all have the same number of valence electrons. So oxygen here has the same number of valence electrons as sulfur, but they have different number of electrons as a whole. And since it is 1 below, it would have another shell. It would have one more shell of electrons. And how did I know that? So over here, we have 1 shell. In this period, all of these would have 2 shells. All of these would have 3 shells. So it's really easy to look at this to determine how many shells that we have. So in this case, we have 2 shells in the case of oxygen. Okay. So now that we understand that, we can look at to what bonding is. So what happens when our elements are bonded. Okay. So let me pull that picture back up of the periodic table of elements. Okay, so we know that over here we have 1 electron, right? And over here, 1 valence electron, sorry. And over here we have 8 valence electrons. So these are basically satisfied with the octet rule. They're not very reactive. They just don't want to react. They're chilling by themselves. But over here, sorry about that. Over here, we have 7 valence electrons. Now, what do we know about the octet rule? The octet rule says that these elements want to have 8 electrons. And they have enough protons to be able to attract that 8th electron. So fluorine, as you know right here, is really reactive because of the fact that it has 7 electrons. It has 7 valence electrons, and it really wants that 1 valence electron. So fluorine is going to be popular with bonding with any of these elements, and then chlorine right here. Obviously, we know sodium chloride, which is our table salt, is really reactive with sodium, and sodium again is also very reactive with chlorine. So this right over here this group right here wants to lose one electron. They want to give up that one electron to someone else who really, really needs it. And over here, this has 7 electrons. Now that really, really wants that one extra electron. So as you can see over there, that is something called electronegativity, that concept that fluorine wants one more electron. So fluorine is more electronegative. So it has a high electronegativity. Let me rewrite that real fast. It has a high electronegativity. And the reason why I'm emphasizing this is because it kind of shows how reactive some sort of element is. Now we know fluorine is very reactive. And these 3 elements right here are also very, very, very reactive. So why isn't this element maybe more reactive? It is really reactive, but it might not be as reactive as fluorine because it has another shell, meaning that it's farther away from the nucleus. So the protons inside of the nucleus are going to have trouble, trying to get that extra electron or the other element to be able to add the electron to itself. So what happens when we see bonding? Zoom out fast. Okay, so now we have let's say we have sodium and chloride, right? We have sodium, and we can represent our valence electron by just drawing our valence electron on top of it, and then we have chloride. So we have 1, 2, 3, 4, 5, 6, 7 valence electrons there, and now it's going to be attracted to that sodium. It really wants that electron from the sodium. So sodium will give up its electron. It will give it up, and chlorine is going to take it. So now chlorine is negative. It's more negative than its stable state, and sodium is positive. Now this creates an ionic bond. It's very, very different from a covalent bond, and it basically puts them together, and we can rewrite this as NaCl, right? And that's our new chemical equation, NaCl, because sodium chloride, and these are really, really, really reacted to each other. They bond together, okay? So this is a bond, not necessarily an attraction force, but that's mainly because this loses an electron and this gains an electron. Okay? So it becomes positive and negative. But what about the case of a covalent bond? What's exactly happening there? So water is covalently bonded, and I didn't want to confuse you with what ionic bonds are, so I wanted to clear that confusion beforehand. So that's why I showed the ionic bonding. But right now, we're going to go into covalent bonds and what covalent bonds are. Now, water is covalently bonded, or the hydrogen and the oxygen are covalently bonded with each other. So let's just draw out a water molecule or so. Okay, switch colors real fast. We have hydrogen, we have an oxygen, we have another oxygen, we have another hydrogen. So H2O. And for now, we'll just draw it however we want. There's no specific structure. For those of you that already understand Vesper structures, just for the demonstration of it right now to make y'all understand the covalent bonds and what's exactly going on, I'm going to get rid of this bent structure shape. But we'll get back to that. So let's look at one of the hydrogen and oxygen bonds. We have H and O. These are bonded together, and there's one line between them. But in the case of when I drew our sodium chloride, we didn't have any lines between them. Well, this is actually supposed to represent the sharing of an electron. And you know how our oxygen has 6 valence electrons, right? Let's just draw that real fast. It has 6 valence electrons, and this hydrogen has 1 valence electron. And now what is happening in a covalent bond is that they are sharing one electron. So now, since they're sharing this electron, they don't necessarily have it, and it's between them. It's going to be going back and forth. And this valence electron, like I said, it will be going back and forth. And so this will act as if oxygen has 7. Because of this sharing, it will act that way. And then hydrogen will act as if it has 2 valence electrons. But it actually doesn't. And that satisfies the octet rule for hydrogen. But now, what about the octet rule for oxygen? It doesn't have all its 8. 1, 2, 3, 4, 5, 6, 7. All of its 8 valence electrons. Now, if I add that in and add another hydrogen, well, now it's going to act as if it's also having 2 valence electrons, and this will act as if it has 8. And this would all be an incorrect representation because technically it doesn't have those extra valence electrons, but it's sharing them. So it doesn't really have it, but it's being shared between them. So this 1 electron is being shared between them. So that's the representation of a covalent bond. That's what's different from an ionic bond, where an electron is being transferred from one element to the other in order to create that bond. And now we have our electron that is bonded. Okay. So now that we understand covalent bonds and what's going on over there, let's talk about the structure of water. And remember how I said that water is a bent structure. So we have hydrogen, we have oxygen, we have hydrogen again. Okay, and that's because of the way that its valence electrons are arranged. So let's take a look at this. And you remember how I said in a covalent bond this 1 electron is being shared, right? So this 1 electron is being shared, and we can imagine that it has that electron here, and we know that oxygen has 6 valence electrons. So let's just say that this electron right here is a part of oxygen. This is also a part of oxygen. Now, how many valence electrons are remaining? Well, 6 minus 2 is 4, so we have 4 more electrons. And these 2 lone pairs of electrons are known as electron domains, and you have your bonds here. And due to this repulsion of electrons, because we know that electrons don't like being near each other, right? And because of this, we have this Vesper shape. And we'll get more into Vesper shapes and so on and so forth, maybe in another video. But as of now, you just need to understand that oxygen is bent. Okay, so what does that mean when looking at our water molecule, right? Okay, in order to show you this, we'll go back to the concept of electronegativity, and I will show you an electronegativity chart. Okay, so here we have our periodic table of elements again, but this is modified. It's to show you our electronegativity values. And remember how I said fluorine has a very, very high electronegativity value, right? It has a value of almost 4. So that's really, really high. And you'll notice that nothing else has that value, and that's why this block is colored really red. Okay, so over here we see that oxygen has an electronegativity value of 3.44. Hydrogen has an electronegativity value of 2.20. Now, let's go back to the concept of a covalent bond. We said that the electrons are being shared, right? But do those sharings need to be happening equally? No, they don't have to be happening equally. Now, we see that hydrogen has a lower electronegativity value. It doesn't really want that extra electron as badly as oxygen does. It really wants the extra electron. So what does that mean in terms of our water molecule here? Well, if we look at this water molecule, since oxygen is more electronegative, it's actually partially negative. Creates this partial negative charge over here, and then our hydrogens here are partially positive, and this symbol right here is our delta. It's our lowercase delta, and this one has a partial positive charge once again. So we know that the electron wants to spend more time with oxygen rather than with hydrogen, and that creates something called a dipole moment. So we can represent that by showing this an arrow showing the direction and this line. Okay, so dipole moment. Okay, so there is a dipole moment present here, right? So basically, that electron is going to spend more time over there than it will with the hydrogen. The similar case is with this hydrogen and oxygen. So basically, it is way more negative than this, because it's partial positive here, it's partial negative there. Alright, so what does that mean with water and its properties? Well, water, since it has this property where hydrogen and oxygen share these electrons, and they have something called a polar covalent bond due to this dipole moment here. So we're going to rename those bonds. Instead of calling them just covalent bonds, we're going to call them polar covalent. Now these bonds are polar covalent, right? So you have your electron spending more time with the oxygen rather than with the hydrogen, once again. And this creates a phenomenon known as hydrogen bonding, which is an intermolecular force, not to be confused with intra. Intra means between elements. So over here we have our polar covalent bond, which is our intramolecular force. But what about between these water molecules? We're not just going to be able to pick up water and just pick out one molecule, right? Those molecules are way too small. So how do we see water as it is today? It is connected to each other in one way, shape, or form, right? And they're not just going to break apart into molecules in which we can just capture and touch, right? So now, let's just erase all of this over here. Get rid of our notations really quickly. And make sure you have all this down. Okay, we write that partial negative, so it's partially negative. We have this phenomenon called hydrogen bonding, which is an intermolecular force. It's merely an attraction force, okay? An intramolecular force, like how we have over here, is basically kind of permanent, and you would need a chemical reaction for that to change. For intermolecular forces, okay, I'm just gonna write that down, intra. Okay, and then this would be inter. For a physical change to happen, you just have to break these intermolecular forces. And this intermolecular force is caused by these partial charges. And we know that negative attracts to positive. So we can just use that hydrogen over there. The hydrogen. And we know that this is polar covalently bonded to another oxygen. And this is polar covalently bonded to a hydrogen. And let's just write that out. Positive, negative, and positive. Okay. So we have our other water molecule, and this is our intermolecular force. It's also commonly known as IMF, intermolecular force. And like I said, it can be broken with a physical change. So what is a physical change for water? You can heat it up, change it from a liquid to a gas, you can cool it down, and so on and so forth. And that's because of this hydrogen bonding, which breaks. When you have it change from a liquid to a gas, it's actually breaking these forces. It's not a bond, it's a force. Okay, so does everything have this hydrogen bonding phenomenon? No, and this is really specific to water and some other molecules. But water specifically because of its dipole moments and the fact that this molecule is polar, right? Because we have our positive, partial positive here, and then we have a partial negative, and this overall molecule has poles. We have a negative pole here, and then we have a positive pole here, right? And not all molecules have that. And also, they are bonded with a hydrogen. If a hydrogen is bonded with any of these following elements, F, which stands for fluorine, O, which stands for oxygen, and N, it stands for nitrogen, commonly known as fun, you have similar dipole moments, which allow you to have this hydrogen bonding that can take place. So that's only possible if you have any of these three elements that are directly connected to the oxygen, directly connected to the hydrogen, and the hydrogen will be able to create these forces, these intermolecular forces. This intermolecular force, like I said, is called hydrogen bonding. And I really want to stress this, it's really not a bonding like how you see with the covalent bonds and the ionic bonds. It's merely an attraction force. I know that I've said this so many times, but it's really, really important that you understand that. Okay, so now that we understand how water is attracted to itself, what are the properties that are associated with it? Well, since water is very, very, very highly attracted to itself, we have something called cohesion. Cohesion means that water is attracted to itself, and this allows it to basically build on top of each other. For example, if you were to take a metal object, a really small metal object, you can stack water droplets on top of each other. So let's just take or plastic, it doesn't really matter. We just have some sort of plate here, something really, really tiny, and then once we put that water droplet, you'll notice that this water droplet will create some sort of bulge here. That's because of its attraction to itself. It's attracted to itself, and it really doesn't want to, kind of flow out. But eventually, you'll find that if you keep adding it, that force is not strong enough to keep building on top of each other. Otherwise, we'd be able to make buildings of water, but we cannot do that. So it will collapse at one point, and that's because it doesn't have there's no sort of bonding that occurs between the molecules. It's merely an attraction force. And I didn't mention this beforehand, but there are different types of attraction forces. Hydrogen bonding is the stronger one out of the other three. But the other forces can also be stronger. We'll get into that in a later video. But for this purpose, you need to know that hydrogen bonding is very, very strong in the intermolecular forces category. It's not as strong as the covalent or ionic bonds, but it is really strong, and you can break it if you have enough force that is applied upon it. Okay, next we have the concept of adhesion. Now, why does adhesion occur? Adhesion is the attraction force between water and another sort of substance, and that's also because of its hydrogen bonding properties. If another polar molecule was near it, it would merely just try to attract to itself. And that is commonly seen in our test tubes. And I don't know if you've noticed, but we have test tubes, and when we're trying to read our water measurement or whatever it is, the water merely just dips down like this. Why is that? Because the water is attracted to this glass right here. It's attracted to this glass, so it basically defies gravity and goes up. And that's why we read the meniscus, which is the bottom part right here. Okay. And lastly, we have the concept of surface tension. Surface tension is basically the resistance to stretching of some sort of liquid. And water has a nice surface tension, and it can allow for certain bugs to be able to walk on it. We as humans can't do that because we would be putting too much pressure, but certain bugs have been able to adapt to that, and so they can maybe just draw that out. Let's just say this is a bug, and it has its legs like that. Yeah, certain bugs can walk on water. Humans cannot, obviously. And that's merely due to the fact that water has surface tension, and that resistance to stretching is also due to hydrogen bonding. So that's really important. And lastly, we have a really high heat capacity. So water requires more heat to be able to change phases, or like I said here, heat capacity, which means the amount of energy, heat energy, that's required to raise 1 gram of water, or 1 gram of the substance, 1 degree Celsius. So water has really high heat capacity, meaning that it takes longer for water to go from maybe 0 degrees Celsius to 1 degree Celsius, or maybe 30 degrees Celsius to 40 degrees, or whatever it may be. That's also due to the attractive forces that are among these molecules, that hydrogen bonding. That hydrogen bonding keeps it really close to each other, and they don't really excite enough to be able to pull apart and allow for that physical change to occur. But we obviously know that water does change into gas if enough heat is given to it, which is different from other substances. Like if you've ever noticed alcohol, if you've ever put alcohol on your skin, it evaporates almost immediately. But water, on the other hand, doesn't evaporate that immediately. So putting alcohol on your skin cools it down faster, and that's really important to why we sweat. We sweat because, let's just draw a hand real fast. I'm not an amazing drawer or artist. We might be sweating from our arm, right? And we have this water. Maybe I should use a different color to show water. We have our sweat right here, right? And our body is really, really hot, and it needs to dissipate that heat. So the water, or our body, will transfer that heat to the sweat, and that sweat will be able to evaporate and leave our body as water vapor. So it basically takes that heat away from it. And so that's really important there. I hope this was helpful in understanding the properties of water. Thank you.